We had discussed the mixing length model. One advantage of the mixing length model is that it is applicable to all flows. See, because even if you do not know the mean flow, it has dUi by dxj. So you put it in and solve the mean flow equations. The dUi by dxj terms will go on with the other terms because ui has to be solved for. So it is applicable to all flows. So even if there's a new type of flow, but the major drawback is that Lm has to be specified and hence the model is incomplete. Lm depends on geometry of a flow and hence and for a new complex flow specification of Lm requires a lot of guesswork. Guesswork, trials, and maybe iterations. For well-studied flows, Lm is well established. For example, we talked of the Baldwin-Lomax model where we wrote nu t was equal to Lm square times omega ij mean of omega ij to the power of half, and this model can also be applied to shear flows. So, but one of the, if we try to look at physically, if there is any issue with the eddy viscosity, see here again, we are writing the eddy viscosity as a function of the mean velocity. Mean of omega ij is the mean velocity gradient related to that. So the turbulence is coming only if we are able to put it in some form of Lm. Otherwise, we are only using the mean velocity, which of course has to be physical because there's a transfer. We have seen that there's a transfer of energy from large scale to small scale, which causes turbulence. So even if you model it on the basis of large scale, there you will get some physics. But then the question comes, is there some way we can directly get a turbulent quantity involved in this model? Right now, even the Lm depends on the geometry of the flow. You take it as distance from the wall, radius of the pipe, something like that, which again is not, will not be so related to turbulence. So the question we ask is, can we get some turbulence quantity directly involved? And before I go to the next one, again we realize if we are up till this stage of model, we are only solving the mean velocity equation. No extra equation has come into play. So computationally, it's just as if we are solving the mean velocity equation, and the turbulent stresses are being used with the nu theta. Pardon? Three Navier-Stokes and continuity. If it is assuming no temperature and all that. So we have only that, those equations. Now comes the next stage of these models, which we call the turbulent kinetic energy models. And mainly introduced by separately Kolmogorov and Prandtl. The motivation for this is, we know nu t is equal to L star times U star. Now sometimes you may wonder, I should put a constant also. But that constant will be absorbed either in the definition of L star or U star. Okay. So now, in mixing length, just to recap, L star was equal to Lm and U star was equal to du by dy times L star. But this would imply, and this is probably can also be seen as one of the critics of the mixing length model, this implies that if du by dy is equal to 0, then U star will be 0, which implies nu t will go to 0. And this happens at if we look at the turbulence behind the grid in the wind tunnel or at the center line of the jet, du by dy is 0. That means nu t will be 0 at that location. So according to the definition of Reynolds stress will be 0 at the center line of the jet, which clearly is wrong. And similarly, in a wind tunnel turbulence everywhere, there is no mean velocity. So then it says that all Reynolds stress should immediately become 0. But that will not happen. So that is the motivation, that let's try to get some turbulent quantity involved. So then Kolmogorov and Prandtl, their suggestion was put U star, the velocity scale, as c times k to the power of r, where k of course we know is the turbulent kinetic energy. And as I said, this constant c takes care of all the other constants to come. K is equal to half of ui prime ui prime. And then, yeah.
Why is it a problem to have a Reynolds concentration 0 and y equal to 0?
Because Reynolds stresses will also go to 0 then.
But it's not a finite dimension, it's just y equal to 0.
But then when you solve it, that means your Reynolds stress profile will be something like this. See, there's a continuous profile, whereas actually you know the Reynolds stresses are almost like this, and they go to 0 only at the edge of the boundary. So according to this, if this hypothesis were to be strictly correct, this Reynolds stress at this point has to be 0, which will not work out. So at least, so that's what the hypothesis tells you. Then, of course, when you calculate the stresses, maybe they will not go to zero because you have a full equation to solve for and you work it out. But at least from there is something wrong in the hypothesis. And that is why they said that because, so therefore, because turbulent velocity does not always go like the way mean velocity goes. So therefore, we try to introduce something like a turbulent kinetic energy as the scale for the velocity scale in nu-t. So therefore, nu-t will become equal to c times k to the power of half times Lm. Now, if we use this, then this will imply that K has to be estimated. Okay. Now, instead of writing a model for K, what we do is that we solve a model equation for K. So instead of now writing K as some function of mean velocity, we actually solve another equation, another differential equation for K. So you realize the model will become more complex. You have to solve an extra equation. Earlier we were solving only 4 equations. Now a 5th equation has come in K. Still we are assuming Lm has to be specified. Okay. So now these are what we called as the one equation models. Now one means actually it is the 5th equation. But one equation means for turbulence you are introducing an extra equation which earlier was not there. So this is taken as the one equation model. And so the steps in problem for solution, if we use the one equation K model for turbulence are we still have to specify a mixing length. Second step, we solve a transport equation for K. And then we put nu-t is equal to C times K to the power of half times Lm. And using this expression, we obtain the expression for ui prime, uj prime, and then we solve equations for mean of ui and mean of p. Okay. Of course, number B and number E will have to be done together because the equation for K will contain mean velocity. So it is something like you solve the 3 components of the velocity together because they are all intermixed. So similarly, a K equation will also come along with them. It is not that you will solve the K equation independently first and then write nu-t, then obtain ui prime, uj prime, and then feed in. This will be done together till you get a converging solution. Okay.
Per time step you have to get
Per time step, you'll have to iterate it and go for the convergence. Okay. So now here, if we look at it, if we look at it from specification of LM and the solution of model equations, we find mean of ui, mean of p. LM we have already specified, so we know we will get k, we will get nu t, and hence we can finally also get ui prime, uj prime. But it is much easier said than done. Let us look at the k equation, because we have to then ensure the k equation is closed. Is it closed or not? We don't know. What do you expect? Will it be closed or will it be unclosed? The k equation, the way we have seen it.
terms like UI prime,
Ui prime, uj prime. So clearly it is unclosed. So let us first look at the k equation and then see what games do we play with this. So the k equation, if we look at the exact k equation or derived from the Reynolds averaged equations, and this we have done in one of the homeworks. We had derived the equation for ui prime, uj prime. So k is a simpler equation. This equation takes the form plus uj dk by dxj. This is equal to production minus epsilon plus partial tj by partial xj. And let us write the various terms. Production was equal to minus ui prime, uj prime I'm not sure if it was Sij or dy by dxj, but it was of this form. Epsilon was 2 nu Sij prime, and Tj was equal to half of uj prime, uk prime plus uj prime p prime upon rho minus 2 nu uk prime sjk prime. These were the various terms. Now let us see which of these, पहले लिख लो आराम से, just write it down. Now I want you to tell me which of these terms are closed and which are unclosed in this scheme of things, which means we are solving one equation k model. Is the first term partial k by partial t, is it closed or unclosed? What do we mean by closed? Either the term is known or we are solving an equation for that. Are we solving an equation for k? Yes. So this term is closed. What about the second term? Mean of uj dk by dxj. Why is it closed? Because we are solving an equation for uj, mean of uj, and we are solving an equation for k. What about p? It has two terms, dy by dxj, we are solving for this. For ui prime, uj prime, we have the eddy viscosity model, which is equal to ck to the power of half times lm. Lm has already been specified because we are using the k model. So therefore P term is also closed. Now epsilon has got Sij prime, Sij prime. So this is not closed. In the one equation K model, we do not have we have to write a term for epsilon. How we will write it, we'll have to see, but it is unclosed. Is that clear? There is no right so far. What have we got? Eddy viscosity model, nu T, Lm. I wrote all those things, but there is nothing for dissipation. So this is unclosed. What about the Tj term? In the Tj term, Uj prime, Uk prime, Uk prime, there is no equation for this. So this is unclosed. Do we have an equation for Uj prime, P prime mean? No. Our equations are only for Ui prime, Uj prime. So this is also unclosed. The third term similarly is also unclosed. But for the third term, we have seen if Reynolds number is high in the flow, then this term is negligible. So maybe the order of magnitude may be small, but it's still an unclosed term. So the whole of the transport and dissipation. So there are two terms, epsilon and Tj. These terms are unknown. I have also used the term unclosed. So you can use any of these. Now, for epsilon, we know epsilon scales as u prime RMS cube over L0, the length. And so this we will write it as CD times k to the power of 3 by 2 divided by L. So this is the modeling approximation we are making for epsilon. That u prime cube will be k to the power of 3 by 2 of that order, and L0 we take it as the mixing. Okay?
Equivalent from P to chips.
Pardon?
Have you gotten this
Equivalence
from P to chips?
from?
From P to chips.
Well, that could be one way. Otherwise, in this whole course, at least when we have started, even when we did not do what is P, what is this, we always said epsilon scales like U cube upon L, where U cube is the large velocity and the RMS, U prime RMS is of the same order as the mean velocity, or L dot is of the order of the geometry of the flow, which is like Lm. And then now, of course, the constant CD is there. Now, how do we find these constants is another story, or how do we estimate them, but at least we have written it in terms of like this. So this closes the epsilon term. No, this is not this is totally, I should have called it C mu or something. I think the Pope's book uses it as CD. In fact, what you can verify for shear flows, CD will go like C cube, where K was, where U star was equal to, or nu T was equal to C K to the power of half times Lm. I think if you manipulate the equations for some class of flows where you will have to use arguments like P is equal to E and things like that, then you get this form. Okay. So this is what it is. Now, for the transport term, let's look at the transport term. This is, in the K equation, we have partial T by partial xt. This is what we are calling as the transport term. In the heat transfer equation, this is like a Fourier flux term, d by dxj of k dt by dxj. So what we do is to model the transport term. Now there is nothing, we model it as equal to minus a constant times dk by dxj. I'll put in the constant in a minute. But basically we are using a flux approach, that the transport term will go like gradient of K. Okay, because all physical quantities, even viscous stresses, are the gradients of the shear stress. That's how the stress term is modeled. So that is how, because there is in the equation, it is not Tj, it is a gradient of Tj. So there will be a second gradient of K which will come in because of this. So this will be like the K del square T term in the heat equation. Okay, now this constant which we have to put a nu. What sort of a nu should we put here? Nu or nu T? Is this a turbulence term or is it a laminar term? Turbulence term. Because all the terms in Tj are ui prime, uk prime, uk prime. So therefore what we do is, we put in nu T, but just to take care, we also put here a constant sigma K, which is like a Prandtl number for K. Because once again this follows, if you write the heat transfer equation and you write nu, then you say nu divided by a Prandtl number. That is what makes it alpha. Okay, so that's why we write it, nu was actually for the mean velocity. So we write it as nu T divided by sigma K. Normally sigma K will be taken as 1. But just in case, if you come across some other flow, things don't happen, so they took it as minus nu T upon sigma K. So here now, let's write it, nu T is the same eddy viscosity and sigma K is a Prandtl number for the turbulent kinetic energy. And what this tells you is that this right hand side is flux of K, which is going down the flux of K is related to the gradient of K. And here basically what you do is, this equation, this sort of a term helps in smoothening the equation, because this is a second derivative and there is a flux which is going down. So if the equations are having a particular shape, this will help. It is in some sense creating some more dissipation for the equations. So in the quantity will tend to get smoothed out at the boundaries because of this term. Because even if you look at the heat transfer equation, if you don't put this term or you put this term, the effect is to basically smoothen out the expression of quantity. So basically the equation being solved for K is, so when I put this, all of this equation is partial K by partial T plus mean of Uj partial K by partial Xj is equal to d by dxj of nu T upon sigma K dk by dxj plus production minus Cd times K to the power of 3 by 2 times Ln. K to the divided by Ln था कि times U cube on L. नहीं, the equation epsilon सीधा ही आएगा ना, divided by आएगा. Okay. Now, of course, the boundary conditions getting on K will not be difficult, because on solid surfaces, etc., K will be 0. And so if there's a no slip condition, then K will be 0. If there's a boundary, then you will assume the derivative is 0 at the boundary, things like that. So that is how it is done.
In the no slip condition, does it also take care of perpendicular to the boundary?
The no slip tells you, so derivative will not be zero perpendicular to the boundary, but the no slip takes care of the total velocity vector is zero. So therefore, even Reynolds stresses will be zero on the boundary, on a solid boundary.
But particles can uh, just ram into the wall and go back, right?
Yeah, they can, but on an average, see that would be at a molecular level. On an average, that is what the no slip boundary condition is, and probably it is, again, we don't have a proof. The tangential component is zero. It is an assumption, and it is sort of verified by experiments. That is all what we can say. And there are, at least in the laminar case, whenever we teach it, we say that there is, if you look at flow of supercooled helium on a surface, it has a slip velocity. Or even in microchannels flow, when you look at it, there could be, if you coat the surface with a hydrophobic coating, there could be a slip velocity. So slip velocity is not to be taken for, no slip cannot be taken for granted, but it is found in most cases. But once again, the biggest drawback of this model is this quantity Lm. The major drawback is Lm has to be specified. So can something be done for this? That means you will say you write an equation for Lm. K का तो लिख दिया, अब Lm का भी लिख दो. ठीक है? So now what one does is, instead of writing, and this is accommodated by what we term as the K epsilon model. In K epsilon model, we call it as a two equation model, where model equations for two turbulent quantities are solved. Now, a length scale dimension is, we have already seen, k to the power of 3 by 2 divided by epsilon will give us a dimension of length, and a time scale dimension will be k upon epsilon. If you look at k upon epsilon, we saw it in the two classes before, we called it the turbulent time scale, is a time scale. So on the basis of these two, what one can write is the dimensions of nu t will be the same as the dimensions of k square upon epsilon. So that means we will write nu t is equal to some constant times k square upon epsilon. Okay? And now to get k and epsilon, we will have to solve equation for k as well as for epsilon. So nu t will be taken as some constants from k epsilon, and we write it like this. So now, first when we try to see, this is a complete model, because do not need to specify any LM, etc. But we need the value of the model constants. They will be needed. Now this model, K epsilon model, was given by probably first time it came in the complete form was by Jones and Launder. Of course, people have been trying different variations, but first time it came as a K epsilon model was by Jones and Launder. And Launder and Sharma in 1974, they gave the value of the constants which are coming here. And so the methodology in K epsilon equation is solve an equation or solve the equation for K, solve the equation for epsilon, and nu t is then written as C mu K square divided by epsilon, and you solve these. And then you go to the mean equation, then solve the mean equations. Okay. Now, of course, certain things which are coming, that if K square is going to 0, or rather if epsilon is going to 0, then K square should also go to 0. Otherwise, nu t will blow up. So some of these things will have to be ensured when you, or when the model and equations are getting solved. You may sometimes get blown up solutions, etc. But before that, if I am solving the K equation like this for the K model, one equation model, what changes do I make here in the K epsilon model? Or do I use the same equation? No, I'm not saying how do you get the epsilon equation. What I'm saying is I'm solving this K equation, this is the K equation. This is when I use it for the one equation model. Now when I use the K equation in the K epsilon, do I make any changes to this or do I solve the same equation? Last term will be epsilon. Now I don't need to model epsilon here. So the last term will be replaced by epsilon. All other model has to stay. Okay. So when I solve the K equation in K epsilon model, the last term will be replaced by epsilon. So let's write this down. So when we solve the K epsilon model, we do not use epsilon is equal to CD times K to the power of 3 by 2 cube upon L. ये मैंने दोनों जगह LM मल्टीप्लाई करके लिखा हुआ है K to the power of 3 by 2. ठीक है. We do not use epsilon is equal to CD to the power of 3 by 2 times LM. Rest is the same. So K epsilon, K equation, we have seen what it is. Now comes the biggest problem. Well, how did we get this original K equation? I already told you the K equation did not come from anywhere. It was from the Rand's equation. We have already derived the K equation. And then the complex terms we have put a convenient model. Now what about epsilon? How do we get the equation for epsilon is the biggest problem. CD K to the power of 3 by 2. How? ये पता नहीं मेरे नोट्स में LM मल्टीप्लाइड लिखा हुआ है. I'll have to check it up, but I don't see. It has to be U cube upon L. It's okay. I think I made a mistake while I was copying my notes. Maybe it is to the power minus 1. So. But how do we get where one complex way will be, which we don't do. Epsilon was related to this. Mean of du I prime by dxj, du I prime by dxj. So I can write an equation for du I prime by dxj multiplied by ui prime or uj prime, and then from there I can get an equation for epsilon. But it will be complex because uj prime itself is a complex equation multiplied by another uj prime, and then or basically no, you have to du I prime by dxj. First you have to take a derivative of that with respect to xj, and then multiply it by itself, and it will be just. So what we do is as modelers or as people in the community, we try to look at equations of all the quantities. And as he said, the equations, all of them have a same form. You look at the equation for mean velocity, it has exactly this form with k replaced by mean velocity and this term being replaced by the new laminar term. Then there is, if there's a pressure term or something, whatever is causing that. Similarly, I look at the k equation. So first there is partial k by partial t plus mean of uj partial k by partial xj, plus there is a derivative of there's a transport term, and then there will be a production term and a dissipation term. So typically everything which is there, for example, even pressure, etc., you can call them as a part of production term in the laminar flow equations. So our equation for any quantity is of this form. So here what we have is, so let me write this. So equation for any quantity is of the form. So now let me call this quantity phi is of the form now, of course, whether this is the mean velocity or the instantaneous velocity, that depends, but typically it's a convective derivative and an unsteady term, and then there's a transport term, a production term, and a dissipation term. And in fact, this sort of a thing, even when you write CFD codes, it becomes very sort of, you write everything like this. Even the continuity equation and all are written in this form, and then you make some of those terms zero to get the exact equation. Okay, so that is the standard way of writing anything. So if we use this, so using this, the epsilon equation becomes partial epsilon by partial t plus mean of uj Yo. Yeah. ये वाली अच्छा
So the condition that we get when the epsilon, when epsilon goes to 0, they are to
हाँ.
So when does the epsilon go to 0?
When does epsilon go to 0? Well, probably it will go to 0 when you are at the extremely small scales. When turbulence is, when basically it actually doesn't actually go to 0. There also it is of order 1 only when the other quantities are much higher. So actually, probably epsilon will not go to 0, but it may happen numerically it goes to 0 when you solve the equation. But otherwise, physically, epsilon will be some order still. It will never be 0. And
Epsilon is dissipation, right?
yeah.
Far end.
So it will become, no, far end, why should it? Because no, it will depend on how the flow is mixing. See, once the flow is laminar, then epsilon will go to 0. There will be no. So there also, because we have when we have an intermittent flow, so then it once we go to this thing, epsilon goes to 0, but then there k also will go to 0. And then somewhere we'll have to probably put that k as to 0, go to 0 faster than epsilon. Maybe some sort of a condition may have to be imposed numerically when you are writing your codes so that you don't have a blow up of Newton. थोड़ा ऊपर करो. So now this is, in this equation now you realize this P is still the turbulent production, but then in the equation we have d epsilon by dt. So the dimensional matching comes by putting this as epsilon, production is the same dimension as epsilon. So I have to put a d by dt. There is a t and t is k upon epsilon. See, production has the same dimension as that of dissipation. But then it is d epsilon by dt, so therefore there has to be a time in the denominator. And that is k by epsilon. So dimensionally everything, see, when you write a model equation like this, you have to ensure that physics is being followed, but before that, you have to ensure that every term is dimensionally consistent. So here, of course, epsilon, C epsilon 2 is a dimensionless constant. This is a dissipation term, so we put minus. Epsilon is basically the dissipation, and then epsilon upon k is time, 1 upon time. So that is why it takes the form epsilon square upon k. So this term is the transport of dissipation, this is the production of dissipation, and this is the dissipation of dissipation. Okay. So now, of course, you may say that this is all your mind's creation. But actually, when we write the equation for dissipation in a complex way, it takes a form like this. It gets a transport term and this. So it does, when you work out the complex equation, you do see some of these terms. But this seems to be the way to go about this. And this makes it the epsilon equation. Now, the whole set is closed because the transport term, we have already put it in terms of this. We need to specify sigma epsilon, and production is already closed. Dissipation, we are solving for it. So that is also closed. So this is the total k epsilon equation. This term is the transport term, transport of dissipation. This is the production of dissipation, and this is the dissipation of dissipation. And what Launder and Sharma found out or worked out was C mu is equal to 0.9, C epsilon 1 is equal to 1.44, sigma k is 1, sigma epsilon is equal to 1.3. So this is what was Launder and Sharma's contribution. They came up with this. Now, one of the questions you will have in mind is, how do we get these constants? A very fair question. We have to look at that. But before that, now suppose with given this K epsilon model, you come across a situation where the flow, you have no idea about the flow. Let's say you have to model flow in a box where there are many chips mounted, things like that. It's a complex geometry and you want to model this flow. Now you don't have any mixing lengths for this, because mixing length, should you take it from the base or the distance from the chip? What you take, you have no idea. You can model this geometry. You can do CFD for the mean velocity. At least you can try and make a grid and solve it. You have an equation for K, you have an equation for epsilon. So now you don't need as such the geometry except to provide the boundary conditions. And you can now solve any equation for any case, putting this equation and trying to solve for this. So in that sense, this model is a complete model. So as you see from the years, the first time this equation we got about this was in 1975, 1976. So late, so about 50 years back, roughly. Since then, at least till this model has been a very popular model. Let's say till about 1520s. Even now, if you look at it in industrial flow where computational resources are less, and if nothing else is available, at least for the first estimates, if we have to find the flow, we use the K epsilon model. But now you know what actually is the K epsilon model. The K and epsilons are not something which will be specified. These are solved in the equations, and simultaneously these values are solved with the mean velocity, because this K and epsilon show up in the mean velocity equation also. So you have to together put all of these together and solve this set of equations to be able to solve for the mean flow. But given this, you don't need anything more. Only problem here are finding these constants. They may be different for different flows, and which does happen. So that is the K epsilon equation. Now, one of the ways how we get these constants, C epsilon is probably this one. C epsilon 2 पता नहीं, मैंने लिखी नहीं है. It must be there probably of order 1. I have no idea. I don't remember that, but you can check up from the books and all. So now, one of the ways how we get these constants. See, for example, if I look at now all those objections which we had, if we look at a homogeneous flows where dy by dxj is not equal to 0, all other statistics are not function of xj. Only the mean velocity is allowed to change, is not 0. The mean velocity gradient is not 0, but all other Reynolds stress, etc., their gradients are 0. If we look at a flow like this, then the K equation becomes dk by dt is equal to production minus dissipation, and d epsilon by dt will become C epsilon P times E by K minus C epsilon 2 E square upon K. So for this, you just have to put d by dxj of all turbulence quantities are 0. So therefore the production etc. The gradient terms will go to 0. There's this thing in the convective term, you have mean of uj d by dxj of k or epsilon, so they will also be 0, because k and epsilon meanwhile realize that they are also turbulence quantities. They are means, they are not fluctuations. So they also don't change with space. So this is the form you will get. And I'm trying to tell you, and if in this we put dui by dxj is 0, which is the case in wind tunnel decaying turbulence. So if dy by dxj becomes 0, then P will become 0. So you'll get dk by dt is equal to minus epsilon and d epsilon by dt is equal to minus c epsilon by 2 epsilon square upon k. Okay. So this sort of simplification, so this will lead to dk by dt is equal to minus epsilon. And notice that's why I've removed the partial derivative from k and epsilon. They are functions only of time. This is equal to minus c epsilon to epsilon square upon k. Now here the solution is of the form k of t is equal to k0 t upon t0 to the power of minus n and epsilon t is equal to epsilon 0 t upon t0 to the power of minus of n plus 1, where k is equal to k0 at t is equal to t0 Now, when you feed this in the equations, what you will get is n will turn out to be equal to 1 divided by c epsilon 2 minus 1, and this will imply that c epsilon 2 is equal to n plus 1 by n. And I think this will answer your question. For the decaying turbulence, therefore, now from the experimental data, we get the value of n. And that will give us the value of c epsilon 2. And this was also, I went through this just to tell you how those constants are determined. So you try to pick out situations where only one constant comes. And then you try to find out from experimental data. So again, you will say that we are actually using some data. So then how is the model complete? Because this was our whole thing saying that the model is complete. But then at least here you need only the decaying coefficient, which at least for this particular case is well established. At least you know, and again this may vary, but for the wind tunnel turbulence, you find from the experiments n is equal to 1.3, and this gives the value of c epsilon 2 is equal to 1.77. So this way we work out. So this is just to see, at least now this sort of simplification of equation we should be able to do, given our background in this course. So I'll just write some of the things, give me 5 minutes. This is the simplest, some appraisal if we do complete model with broad range of applicability. Most commercial codes use K epsilon model, and it has also been developed for heat transfer, combustion, multi-phase flows. So similar eddy viscosity model for the flux has been done, and it is quite very this thing. However, this model is inaccurate for, and again in all these the proof is in the pudding. If it really works out well, we check with the results if the model is giving us the right results. And here in complex flows, even mean flows may be quantitatively wrong. And the error comes from two things. Where do you think things will go wrong? One is the Newton term, and actually to find out the Newton term, if you have experimental data, you have the Reynolds stress value as well as the mean velocity gradient. You can divide the two and get Newton. So check up what Newton you are getting from K epsilon model, what is the experimental value. It is found that most of the error which we get is coming because the Newton term is not proper. Or secondly, which equation do you think is the most prone to errors? The epsilon equation. So, or the epsilon equation. So from here, in this course we will not be going, but maybe in the last class, let me see what all I will cover. That's tomorrow. But when you are near the wall, then we need some near wall treatments model. Some extra terms have to be added to get the wall region properly. And you must have heard of a term called law of the wall. You have to use some wall functions, what we call them, to get the wall modeled properly, even using K epsilon model. So this, and sometimes we adjust by changing the value of the constants. Sorry. So we change the value of the constants and we get to this. So these are just some appraisal. Now there's one more term which keeps on coming and I'll just state that. So just there's something called RNG K epsilon model. Has anyone heard of this or seen this term before? No. If you use any commercial package like Fluent, it gives you options to choose. It will tell you K epsilon model. Along with that, it will also show you RNG K epsilon. And you're not very sure which one to use. But what RNG does is, RNG is renormalization group theory. So this was, there's a Russian scientist Yakov who was at Princeton, and he used RNG to get K and epsilon equations from the Navier-Stokes equations. So he used a totally different approach which is used in plasma physics and all, the renormalization group. I don't understand this, I'll be honest about it. But when he did this and he worked out, he got slightly different constants. C mu was 0.0845, C epsilon was 1.42, C epsilon 2 was 1.68, sigma K and sigma E were 0.72, and there is an additional term in the epsilon equation. So this is the difference between the RNG K epsilon and the K epsilon model. Now sometimes people use RNG K epsilon, others use K epsilon. Sometimes they compare the both, they find similar results. But all this keeps on happening. This is the K epsilon model.
The difference between what you have done in the class and what Yakov did is he rank and he used.
Not right. He used the Navier-Stokes equation and he used renormalization group theory on the Navier-Stokes equation. And using that, he derived the K and epsilon equation. And the constants he got were different. I think in this renormalization group, the constants automatically flow out. So what we showed was we just made up an epsilon equation. Actually, our epsilon equation is not made using ranks. It is just a contrived equation, you can think of it. It is just a balance equation. We have used some sort of a knowledge base to build up an equation for it. Yacob did something similar, so that's why he claimed that his work is more accurate. But his epsilon equation has an extra term. And he got these constants. So, well, I remember when I was a graduate student in late 80s, there were these conferences where Yacob would come. And other people very sarcastically would call him God Yacob. Because he used to behave like that he is the one who knows everything. No one else knows anything else. So, he used to call him God Yacob. So there were interesting conferences and he would just say, no, everything else is wrong. But so the only thing is that the assumptions under which these were derived may not be very valid to turbulence. So, but then at least, so this was there. Now in tomorrow's class, we'll still have tomorrow's class. It's not that we'll not have it.
Even in these, the values are not way off from.
They're not very way off. That's right. So that's fine. From the experimental values which Sharma, Launder and Sharma got. And then people keep on changing. See, sometimes you have a flow with curvature. Then you will use some other values. You will put a curvature term also in the equation. So sometimes even you modify the K and epsilon equations, put some extra terms there like with curvature and all. That is done. And I'll talk of some more variations of these models tomorrow. And then there is at least. So then there's one more thing which comes in which probably goes with today's class, but we'll discuss it tomorrow, is that in 1990s, early 90s or late 90s, what Spellart got this idea. And what he said was, instead of doing all this, why don't I write an equation for nu t? So then I don't need K, I don't need epsilon. I just write the equation for nu t. How do I write the equation of nu t? The way the equation of epsilon has been written. So he wrote an equation for nu t. And they solved many problems. And that model is called Spellart-Elmaras model. Now, how much equation? That's a one equation model. But it is a one equation complete model. Because you don't need any mixing length. So, what Spellart and Elmaras did, they just wrote the equation for nu t. That also worked. So, many things could work. But then also in tomorrow's class, I'll tell you what the next higher step in this Reynolds averaging equation. We'll not go through those models. And then briefly, I'll talk about the LES model, what exactly it is, but very little. I don't even think we'll be able to go to LES at all. But at least I'll give you where it stands today. Now for the exam,